Let us solve this important definite integral. So here we have to evaluate the integral that is from 0 to 76 pi, and here the integrand is mod of sine x, that is the absolute value of sine x. So let us first call this integral as I, right? So here in order to evaluate this definite integral, we have to make use of the concept of periodic function, right? So here we have the integrand mod sine x. So let us take the function that is f of x is equal to mod sine x, and from trigonometry we know that the period of sine x is given by 2 pi, right? And the period of mod sine x is given by pi, right? So period of sine x is 2 pi, and period of mod sine x, which is our integrand, is pi, right? So we can now write this integral as I is equal to 0 to 76 pi. So we can now write 76 times pi, and here we have mod sine x and dx. So let us denote the period of mod sine x as t, right? And here we are going to make use of an important property of definite integrals involving periodic function, right? Suppose we have a function, say g of x, which has a period, say t, right? So the integral that is 0 to n times t dx is given by n times the integral from 0 to t, and here we have g of x dx, right? So this is an important property of definite integrals, where g of x, that is the integrand g of x, is a periodic function which has period t, and here n is an integer. So the value of the integral that is from 0 to n times t g of x dx is equal to n times the integral from 0 to t g of x dx. So now if we compare this integral with this one, then we can see that g of x is mod sine x, that is f of x, right? And mod sine x has period pi, and here we have the period pi that is equal to t, right? So now this integral is of this form: 0 to 76 times t, that is here we have t is equal to pi, and here we have mod sine x and dx. So using this property we can now write, because the value of n is equal to 76, so we can now write 76 times the integral from 0 to t, right? And t is equal to pi, because the period of mod sine x is pi. So here we have pi, and here we have g of x dx, that is simply mod sine x and dx. So this integral, that is 0 to 76 pi mod sine x dx, is now equal to 76 times the integral 0 to pi mod sine x dx. So now we have to find out the value of this definite integral using the definition of mod function and the sign convention of trigonometric function. In this case it is sine x in the four quadrants. So now the definition of mod function can be given as mod of p is equal to positive p whenever p is greater than 0, mod of p is equal to 0 when p is equal to 0, and mod of p is negative p when p is less than 0. So here we have for p we can write sine x. So mod sine x is now defined as positive sine x whenever sine x is greater than 0, and mod of sine x is equal to 0 when sine x is equal to 0, and mod of sine x is equal to negative of sine x whenever sine x is less than 0. So now here we have the four quadrants. Here we have 0, here we have pi by 2, this is pi, this is 3 pi by 2, and here we have 2 pi, right? And from trigonometry we know that the sine function is positive in the first and second quadrant. So this is first quadrant, this is second, this is third, and this is fourth. So sine function is positive in the first and the second quadrant and negative in the third and fourth quadrant. So here we have sine x greater than 0, right? So sine x is positive in the first and second quadrant. So we can here write when x belongs to either the first quadrant or the second quadrant, then sine x is positive or it is greater than 0. And sine x is equal to 0 implies that x is equal to n pi, where n is an integer, right? So now sine x is less than 0 when x belongs to the third or fourth quadrant, right? So from here we can now write sine x is less than 0 when x belongs to either the third quadrant or the fourth quadrant. So sine x is greater than 0 when x belongs to first or second quadrant. So we can now here write when x belongs to the interval that is from 0 to pi, right? And here sine x is less than 0 or sine x is negative when x belongs to third or fourth quadrant. So from here we can write x belongs to the interval that is from pi to 2 pi, right? So here we write pi to 2 pi. Now see, here we have to find out the value of this integral from 0 to pi. So here x belongs to, or x varies from 0 to pi, right? So here x belongs to either first or the second quadrant, and in the first or second quadrant we have mod sine x is equal to positive sine x. So we have now 76 times. Here we have 0 to pi, and here we can write simply positive sine x dx, because mod sine x is equal to positive sine x when x belongs to the first or the second quadrant. So now we can easily find out the value of this integral, and we know that the integral of sine x is negative cosine x, and limits of integration are from 0 to pi. So we can now write 76, and here we can take this negative sign outside, and we have cosine x, and limits of integration are from 0 to pi. So we have minus 76, and here we can first substitute pi for x and then 0 for x, and we'll take the difference. So we have cos pi minus cos 0. So we can now write minus 76, and here cosine pi is minus 1, cosine 0 is 1. So we have now minus 76 times minus 2, and that is equal to positive. Here we have 2 times 6 is 12, and here we have 2 times 7 14, that is 15, right? So the value of this definite integral is equal to 152. So I is equal to 152. Hello viewers, in today's session we are going to discuss another important and conceptual problem from limits, where we have this function y is equal to f of x, that is equal to greatest integer of x minus 1 divided by a signum of x minus 3. And we have to discuss the existence of the limit of this function when x tends to 0, right? So here we have this function y is equal to f of x involving the two important functions in mathematics, that is the greatest integer function and the signum function, right? So here we have to see whether the limit x tends to 0, f of x it exists or not. So now this limit, that is limit x tends to 0, f of x it exists if the right hand limit and the left hand limit of this function y is equal to f of x when x tends to 0, both these limits are finite and they exist, and moreover these two limits should be equal to each other. So this limit is going to exist if the right hand limit it exists, the left hand limit it exists, and both the limits are equal to each other. So let us first find out the right hand limit of this function when x tends to 0, and then we'll find out the left hand limit of this function when x tends to 0, and then we'll try to draw the conclusion whether the limit of this function when x tends to 0 it exists or it doesn't exist, right? So the existence of limit of this function when x tends to 0, it depends on the values of the nature of right hand limit and the left hand limit. So this limit exists if the right hand limit exists and the left hand limit exists, and both the limits are equal to each other. So now the notation for right hand limit is given by limit, and here we have x tends to 0, and here we put a positive sign, and here we have f of x. So we can now write limit x tends to 0, and here we have f of x, that is greatest integer of x minus 1 over signum of x minus 3. So now to get the value of this limit, let us make this substitution, that is x is equal to 0 plus h, where h is infinitesimally very small quantity, right? And moreover h is greater than 0 and h lies between 0 and 1, right? So if we take x is equal to 0 plus h, that is x is equal to h, and when x tends to 0, then h tends to 0, right? So now we can write this expression in terms of h. So we have a limit, and here we have now h tends to 0, because we are taking x is equal to 0 plus h, that is 0 plus h, which is equal to h, and when x tends to 0, then obviously h also tends to 0. And remember, h is a positive quantity and it is infinitesimally very small. So here we have now limit h tends to 0. Here we have for greatest integer of x, we can now write simply h, or 0 plus h, which is equal to h, and here we have minus 1, and here we have signum of h, and here we have minus 3, right? So now here let us apply the definitions of greatest integer function and signum function, right? Now see, signum function is defined like this: signum of x is equal to positive 1 whenever x is a positive quantity, that is x is greater than 0, and signum of x is equal to 0 when x is equal to 0, and signum of x is equal to minus 1 whenever x is a negative quantity, that is x is less than 0, right? So now here we have greatest integer of h, right? And h is infinitesimally a very small quantity, but it is positive, and h it lies between 0 and 1. So by definition of greatest integer function, the greatest integer of h should be equal to 0, because here we have 0 and here we have 1, and h is infinitesimally very small and it lies between 0 and 1. That is, it is very close to 0, right? But it lies between 0 and 1, so the greatest integer of h should be equal to 0, right? And here we have signum of h. Now signum of h is equal to plus 1, because h is a positive quantity, right? H is positive, therefore signum of some positive quantity should be equal to plus 1 due to this definition, right? So whenever x is greater than 0, then signum of x is equal to plus 1. Here h is a positive quantity, so signum of h takes the value plus 1. So now we have limit h tends to 0, greatest integer of h is equal to 0. Here we have minus 1, signum of h is equal to 1, and here we have minus 3. So now this term is independent of h, so we can now drop this limit notation. We can omit this limit notation. So we have now simply 0 minus 1 over 1 minus 3, that is minus 1 over minus 2, that is equal to half, right? So the right hand limit of this function when x approaches to 0 is equal to half. So let us now find out the left hand limit. So now the notation for the left hand limit is given by limit x tends to 0, and here we put a negative sign, and here we have f of x. So we can now write limit x tends to 0, and here for f of x we have greatest integer of x minus 1 over signum of x minus 3. So now here we can make this substitution, that is x is equal to 0 minus h, right? And again h is infinitesimally very small, but it is a positive quantity, so we can now write x is equal to 0 minus h, that is equal to minus h. So now when x tends to 0, then h also tends to 0, right? So we can now write this limit in terms of h. So we can now write limit h tends to 0, and for greatest integer of x, we can now write for x we can write minus h, and here we have minus 1, and here we have signum of minus h and minus 3, right? So now here we have to find out the value of greatest integer of minus h and signum of minus h, right? Now see, h is a positive quantity. So when h is a positive quantity, then negative h is a negative quantity, right? So here minus h is a negative quantity, and for negative quantities, that is when x is less than 0, signum of x takes the value negative 1. So here we have minus 1, and here we have greatest integer of minus h. Now see, when h is infinitesimally very small and it is very close to 0, then h lies between 0 and 1. So the greatest integer of h is 0. So now here we have minus 1, and minus h is greater than minus 1, but it is less than 0. So minus h is lying between minus 1 and 0, because we can obtain this inequality by multiplying this inequality throughout by -1, and the direction of the inequality get reversed, right? So minus h is greater than -1, but it is less than 0. So we have minus h somewhere here and a positive h somewhere here. So by definition of greatest integer function, the greatest integer of minus h, here we have minus h and here we have plus h. So minus, the greatest integer of minus h is equal to minus 1, and the greatest integer of h is equal to, here we have 1, and the greatest integer of h is equal to 0, right? So now we can write here limit h tends to 0, and for greatest integer of minus h we have -1, then we have -1, and signum of minus h is -1, and here we have -3. So now this expression is independent of h, so we can omit or we can drop this limit notation. So we have simply -1, -1, -1, -3, and here we have -2, and here we have -4. So we have now 2 over 4, and that is equal to half. So the left hand limit of this function when x approaches to 0 is also equal to half. So from this discussion we can see that when x approaches to 0, both the limits, that is right hand limit and left hand limit, both are finite, they exist and they are equal to each other. That is, right hand limit is equal to left hand limit, that is equal to half, right? So we can now claim that the limit x tends to 0, f of x, it exists, and the limit of this function when x approaches to 0 is equal to half. So the value of limit x tends to 0, f of x is equal to half. So viewers, this is how by the concept of right hand limit and left hand limit, we can prove the existence of limit of a function at the given point.